All right, this is a continuation of the types of reactions video. Today we're talking about single replacement, double replacement, and combustion. These ones are a little bit trickier. Combustion, not so much, but it's what we got. All right, we're on to the third type of reaction, single replacement. This is where things get a little bit more difficult and require a little bit more attention. Right? I sometimes call this the home wrecker reaction because there's a single element breaks up a pair. Right? These two are in a relationship. We call them bonds in chemistry. But A comes by and is looking at C. A switches with B. Relationship swap. B got home wrecked. All right. Just a funny way to remember it if you need something. Okay. The key thing here is that cations replace cations. Usually this means metals replace metals. Or anions replace anions. This usually means nonmetals replace nonmetals. There's an exception here, hydrogen, who is very special and always is an exception. All right. So the cation, usually a metal, or anion, usually a nonmetal of a compound, is replaced or swapped with a different cation or anion. All right. It follows this general pattern of element plus compound gives compound plus element. Okay. So we see that pattern. All right, let me color code it for you. Element plus compound gives compound plus element. Element plus compound gives compound plus element. Element plus compound gives compound plus element. Right? Which element is on the outside, all right, depends on what you're swapping it with. Okay, so we take a look here. All right, lithium is a cation, a metal. It has to replace the metal or cation part of this compound, which is calcium. Calcium is the metal part. Right? If we were to look at this next one, potassium is a metal. It's a cation. It has to replace the metal cation part of this one, which is magnesium. Okay. Calcium is a metal cation. It has to replace the cation part of this one. Hydrogen is actually a cation here with a +1 charge, even though it's a non-metal. It can sometimes behave like a metal with its charges. So that's a weird swap one. But otherwise, everything works out as metal swaps with metal, non-metal swaps with non-metal. All right, so we see that continuing. Fluorine, or fluoride if it's an ion, switches with bromine, or bromide if it's an ion. So non-metal replaces non-metal, anion replaces anion. Non-metal here, chlorine replaces non-metal here, bromine. Anion replaces anion. So we get a swap, and we get the new compound plus the element that gets kicked out. If it's a diatomic, all right, the diatomics cannot be left alone. They have to be partnered up with at least one of their same kind. All right. So that's why you see all of these, F2, Cl2, H2, Br2, okay, plus a few more. All right. Those ones can't be alone. They need a buddy. They need a partner. If you did want to balance these, this is the way this works out. Again, not graded on the test, but I will show you. Okay, so if we wanted to predict these, all right, these ones can be a little bit tricky because it asks us to identify metals and nonmetals first, deciding what swaps, and then making our formulas. All right. So here, let's look at this color coding first. Actually, let's look at the diatomics. We got F2, we got Br2. These ones have to be diatomic. They can't be alone. But cesium, CS, magnesium, those ones can be alone. They're fine. Okay. So here's the color coding so you can follow along, make it a little easier for yourself. Okay. In this case, cesium is a metal. It's a cation, so it swaps with the metal cation part of this, which is sodium. And if we wanted to do that, we would get instead cesium iodide instead of sodium iodide. So in this swap, all right, crisscross method, you can use, the not necessary here. You get cesium iodide, and then sodium is left alone. It's not a diatomic, tetratomic, or octatomic. It's not any of those. So it can be alone. That's okay. All right. If we look at this next one, all right, fluorine is a nonmetal, has to swap with the nonmetal part of this one, which is sulfur. All right, so if we wanted to do that, in this case, lead is actually a 4+ ion here, which is on your ion chart. Don't worry too much about that. And then fluorine is fluoride, a -1 ion. So if you wanted to switch these together, you would get lead tetrafluoride, right, which you could actually call lead 4 fluoride. All right. So notice here, sulfur can't be left alone. It's actually octatomic. Otherwise, everything works out okay. Okay. In this case, bromine's a nonmetal, has to switch with the nonmetal part of this compound. So nonmetal switches with nonmetal. You can do the crisscross method here, not necessary though. And you get KBr plus I2. I2 is one of those diatomics, can't be left alone, always comes in a pair. All right. Next one, magnesium is a cation. It's also a metal. It'll swap with the cation, which in this case is hydrogen. Happens to be that it's not a metal, but hey, that's the way it works out. This is why we always write our ionics with the cation first, so that this switch always works out. Okay. If you wanted to do this swap, all right, magnesium is 2 plus, chlorine is 1 minus. Crisscross method works out. You get MgCl2, magnesium chloride, and then you get hydrogen, which is a diatomic, can't be left alone. Last one here, magnesium, the cation, will switch with lead, which is also the cation. They also happen to be both metals, which is usually the case. Metal swapping with metals, now we'll get magnesium paired with nitrate. So if we take magnesium, which is 2 plus, and nitrate, which is 1 minus, crisscross method, find out that you need 1 magnesium and 2 nitrates, and that works out fine. Lead is left alone on the outside. It's not diatomic, tetratomic, octatomic, any atomic. It's just monoatomic. It can be left alone. Okay, so if you wanted to balance these, this is the way this would look. Again, not on the test, but it is here for you. Okay. Double replacement is where things get a little bit more challenging, because here it's asking us to do the crisscross method multiple times per reaction. But if you've been following along and you know your crisscross method, things are probably going to be okay for you. All right. So start out with color coding this along with our color coding system. So some compound plus some compound gives us some new compound and another new compound. So the pattern here is compound plus compound gives compound plus compound, which try saying that 5 times fast. It's really tough. So cesium sulfate and aluminum chloride. All right. In this case, we have a switch. All right. So cesium comes to swap places with aluminum, but aluminum takes the place of cesium. So there's really a double replacement. So cesium gets replaced and aluminum gets replaced to make 2 new compounds. So in this case, we can keep going though. Metals swap with metals. This always works out fine, but you can also consider it cations swap with cations. Or if that's too difficult, you can think first element of first compound swaps with first element of second compound to give 2 new compounds. Right? But we can go down the line and see that this always works out with this switch. Okay? So cesium and aluminum switch places. So instead of cesium sulfate and aluminum chloride, you get cesium chloride and aluminum sulfate. Here, sodium phosphate and iron chloride, you get sodium chloride and iron phosphate. It's just a switch of these first 2 elements. They take each other's places. Okay, so if you did want to balance it, this is what it would look like. Again, not on the test, but I will show it. All right, so if you want to predict a double replacement reaction, here is the way we would go about it. So I'm going to start out by showing that we're definitely switching these first elements here. So sodium and silver switch. Silver's Latin name is argentum, which is why it's Ag. Calcium and sodium switch, calcium and lead switch, calcium and sodium switch, magnesium and sodium switch. I used a lot of calcium here. All right. So color coding, if you want to follow along. But if we take it, all right, we can take it 2 crisscrosses at a time. So if sodium here is replacing silver over here, we'll get sodium nitrate and silver chloride. All right, so sodium and nitrate, silver and chloride. Don't really need the crisscross method here, but I'll show it just for fun. All right, it's 1 and 1, ends up as exactly the same as it was. So those are our 2 products, sodium nitrate and silver chloride. For this second one, we have calcium hydroxide and sodium bromide are going to be our products. You can use the crisscross method to figure out how many of each you need. You end up needing 2 hydroxides for calcium. Sodium bromide, you don't even really need the crisscross method for because it's +1, -1. All right. So we'll end up with calcium hydroxide and sodium bromide as our products. Next one, when we switch calcium and lead, we get lead chloride and calcium sulfate. All right. For this first one, crisscross is not needed, and if you do it, it'll lead you astray. But 2 plus and 2 minus already cancels out. No need to do anything more. For lead chloride, though, you may want to use the crisscross method. You'll get PbCl2. So those are our products. For the next one, we're switching calcium and sodium. All right, so calcium and sodium switch places. So we'll get calcium phosphide and sodium bromide instead of calcium bromide and sodium phosphide. All right. So if you want to use the crisscross here, you can for calcium phosphide. That works out fine. Sodium bromide doesn't need it because it's exactly the same as it just was. All right. So crisscross works out. We end up with Ca3P2 and NaBr. So those are our products that we'll write down. For this next one, magnesium and sodium are switching places. So instead of magnesium chloride and sodium carbonate, we get magnesium carbonate and sodium chloride, right? You can do the crisscross method if you want. This first one, it'll actually get you the wrong answer. Second one doesn't necessarily matter. But we should know 2 plus and 2 minus, it's already canceled out, perfectly fine. So MgCO3 and NaCl are our correct choices, right? Now, if you did want to balance these, balancing is possible. It's not necessary, it's not graded, but that's what it would look like. Okay, combustion reactions. All right, these ones are actually the simplest overall. So a hydrocarbon, substance usually containing just carbon and hydrogen, reacts with oxygen, O2, to form carbon dioxide, CO2, and water, H2O, and it releases heat. So anytime you see this reaction, it's some sort of hydrocarbon, name hydro and carbon, hydrogen, carbon. Sometimes it includes oxygen, but that doesn't really change much. Always reacting with oxygen, usually from the air, to yield carbon dioxide and water. All combustion reactions that we'll look at for the next several class days, just carbon dioxide and water are the products. And realistically, you could also say heat. These usually make a lot of heat as well. Okay. If you wanted to balance these, this is the way it would look, but the general pattern here is pretty simple. You see a hydrocarbon, something made out of carbon and hydrogen mainly, and you see oxygen gas, again diatomic, can't be alone, so it's O2, not O, yields or produces CO2 and H2O and heat every time. So there's not really a lot of spectacle to this one. If you see a reaction like this is clearly a hydrocarbon made out of carbon and hydrogen. This is clearly oxygen, all right? When you combine the two, you always get the exact same products every time. There's nothing unique about this. It's very predictable. Carbon dioxide, water, heat, done. Okay. So if you go through, you can balance this. These ones are actually kind of painful to balance and take a lot of mental gymnastics. But if you want to, they are totally possible, and this is what you would get. Well, hey, that's it for now. So if you want to try taking the checkpoint quiz, please do go ahead.